In this video, we're going to start learning about the concept of stoichiometry. By the end of this lesson, you'll be able to use mole ratios to solve a variety of stoichiometry problems: mole-mole, mass-mass, mass to particles, particles to mass, and other type of stoichiometry problems. These learning goals will make a lot more sense to you once you've actually tried some stoichiometry problems yourself using the examples going forward. As usual, there's some great preview the materials videos that you can watch ahead of time to make sure you're familiar with some vocabulary going into the lesson, and also to get some great examples, applications, and different perspectives of the material. Before we go into full-out chemistry that you would see in stoichiometry that you would see in chemistry, let's do something more relatable. Let's do chemistry in the kitchen, because we all love eating. So here's a recipe challenge. And I want you to think about how you would help me solve this problem. So this recipe calls for these ingredients to make 24 cookies, one batch. That's not enough for me. I need more than 24 cookies. I mean, especially if I have to share with someone, I need to make more than that. So let's say I want to make 72 cookies. How much of each ingredient will I need to make 72 cookies? So I want you to think about how you would do that, how you could figure that out. Pause the video, write out how much you would need, and then unpause it to see if you're on the right track to make these delicious cookies here. 72 of them, not 24. So a lot of you probably just said, okay, I want 72 and this much, all these ingredients makes 24. So 72 over 24 is 3. So I'm making 3 times more cookies. So basically I need 3 times each, 3 times the amount of each ingredient. So for example, 6 cups of peanut butter because you multiplied it by 3, 9/4 cups of sugar because you multiplied that by 3, 6 eggs because you multiplied that by 3, and then 3 times half. No, that should be 1.5 cups, 1.5 cups of chocolate chips, because that would be 3 over 2. So that's a mistake there. So it should be 3.5 cups of chocolate chips. Though, I mean, the more the merrier. Put more in there, of course. But if we want to follow the basic recipe, we multiply everything by 3. That's essentially what stoichiometry is. Chemical reaction is a basic recipe to make a certain amount of product. If you want to modify the amount of product that you want to make, well, you need to follow the proportions in your recipe to increase the amount of product you want to make there. So if my reactants make 24 products, well, then if I want 72 products, I have to multiply all the reactants by 3. Whereas if I wanted, let's say, 48 products or 48 cookies, I'd have to multiply everything by 2. That is stoichiometry. At the most basic level, that's what stoichiometry really is, except we're dealing with particular chemicals and chemical reactions instead on a more basic level. So here we can see making a sandwich. This is an example of stoichiometry as well. This is a basic recipe to make this sandwich over here. Two toast slices, 2 turkey slices, 1 lettuce leaf, 1 tomato slice go together to make your sandwich. And if you have other recipes or other snacks you like to make, try to draw out a little equation for your recipe or snack or food that you like to make in much the same way here. And then ask yourself, okay, well, this is to make one of those things, one of these sandwiches. What if I want to make 4 turkey sandwiches? What would I need? And essentially, we just want to follow the same ratios all the time and have everything in the same proportions that you see for the basic recipe here. So if I wanted to make 4 sandwiches, this is for 1 sandwich, you want to multiply your recipe by 4, right? So you would need 8 slices of toast. You would need 8 turkey slices, 4 lettuce leaves, and then 4 tomato slices, or whatever your recipe is. Same idea. If you want to make 4 of that, or 4 times the amount, you'd need 4 times of everything here, following the same ratio, following the same balanced equation at the end of the day. And again, that's what stoichiometry is about. We give you a basic recipe and an equation, and we essentially say, well, what if you want to make this much instead? How much of your reactant would you need? Or what if you had this much reactant? How much of your product could you make? Just following that recipe analogy for the sandwich or the cookies, it's the same thing. So what is stoichiometry? The study of quantitative relationships among the amounts of reactants used and the amounts of products formed in a chemical reaction. What that basically means is you're studying the ratios between the reactants and products in your reaction. And you can use those ratios to figure out how much reactant should react with how much of another reactant, or how much product will be made based on the amount of reactant you have there. Now, what's important is that the ratios you use have to be mole ratios. They can't be mass ratios, okay? Because you want to treat it on a mole to mole level. So there's a relationship in the equation based on moles. These coefficients here are essentially based on moles. So you're saying if you have 1 mole of N2, it'll react with 3 moles of H2 to make 2 moles of NH3. That's what this expresses. Or you can think of it as molecules as well. You have 1 molecule of N2 makes 3 molecules of plus 3 molecules of H2 will yield 2 molecules of NH3. This is your basic recipe. Think of this as like the sandwich. You make 2 of them as long as you have 1 of these and 3 of these. And the ratio always needs to apply. So if I want to make 4 of these, and you might think in your head, okay, if I want to make 4 of these, I need, okay, double. I need 2 of these and 6 of these. So it's the same thing as the sandwich example or the cookie example. If you want to double it, you got to double everything in there as well to make sure the ratios stay the same. But they do have to be the mole ratios, the coefficient ratios that you see here, and the moles that are given to you in a question. So if I ever wanted you to find the amount of moles of product or moles of something, you would first need to make sure you have a balanced equation. You would then make a mole ratio between the chemicals that you're comparing and use a conversion factor to find your unknown quantity. It seems confusing right now, but we'll do some examples to clarify what all that means. So these are the main steps for mole-to-mole stoichiometry problems here. Remember, stoichiometry is essentially just using proportions and ratios to find an unknown quantity in your recipe, in your reaction. That's all stoichiometry really is. So let's take a look at some mole ratios over here. So what is a mole ratio? Because I've said that term a couple times here. So it's a ratio of the amounts of reactants and or products in a chemical reaction. Okay, so for example, if we look over here, we have H2 and O2 reacting. They react in this ratio, a 2-to-1 ratio. You have 2 H2 molecules and 1 O2 molecules in this reaction. You could make a ratio between O2 and H2O. If you have 1 O2, there's 2 H2Os produced. So for every 1 O2, there's 2 H2Os. It's a 1-to-2 ratio. Or you can make a ratio between H2 and H2O. For every 2H2, you have 2H2O. So it's a 2-to-2 ratio between these two substances. Or you could simplify it to say a 1-to-1 ratio, because usually we keep the most simple ratio there. So for every 2H2, there's 2 H2Os made. For every 1 O2, there's 2 H2Os made. For every 2H2, there's 1 O2 that reacts. So 2-to-1, 2-to-2, 1-to-2. And that's our mole ratios. And we need to make sure that we're using, when we do stoichiometry, we have to use mole ratios or particle ratios. That works too, or molecule ratios, but not masses. Okay, the masses don't follow that ratio relationship because all the different atoms have different masses. So we just make our ratios based on counting, and we can count particles and moles, but the masses, they don't follow that ratio relationship. And so where do we determine those ratios from? Well, we use the coefficients in the balanced equation, right? So as I said before, 2-to-1, that came from the coefficient in the balanced equation. That's how we determine our ratios. And then you can use those ratios to predict, how much reactant would be required to make a certain amount of product, or how much product can be made from a certain amount of reactant. So, for example, if I want to make 4 H2Os, I want to maintain the same ratio, so I can just multiply everything by 2, so I can get 4 H2s and 2 O2s, but it's still 4-to-2, which is still 2-to-1 when you reduce it. So the ratios are always maintained in the recipe. Otherwise, if you don't follow the ratios, you're not making the right product in the end. It's kind of like with the sandwich. If I didn't follow the ratio, if I had extra bread, I'd have a sandwich with an extra slice of bread on it. It wouldn't be the product that I'm really looking for. I'd have a wasted piece of bread at the end. So we did do a lesson on ratios and proportions earlier. If you need to review ratios and proportions, I highly encourage you view you click on the link over here as it goes over the lesson we did previously, and it had a video lesson on it as well. So do go over it if you're if you struggle a bit with ratios, to make sure you understand it before going into more detail. So I just want to show you how you can view these coefficients. You can view them in 2 different ways, or 2 main ways. You can view them at the microscopic level or at the macroscopic level. Microscopic. Micro means very, very small. Macro means larger. So microscopic, if I was looking at these at the microscopic level or the molecular level, I could say that this is the 2 molecules of H2 react with 1 molecule of O2 to make 2 molecules of H2O. But when we deal with chemical reactions, we don't just deal with two molecules, one molecule, and two. We deal with big numbers, with moles of them. So at the bigger level, the macro level, the macroscopic level, we can also say 2 moles of H2, because it follows the same ratio, reacts with 1 mole of O2 to make 2 moles of H2O. So you can look at this as the mole coefficients, also molecular or molecule coefficients. It works out the same way because, like I said, the ratios are still the same regardless, since we're just counting. But we're never gonna use mass ratios. Okay. So again, you can use these coefficients to make predictions about how much reactant you need, how much product you can make, or if you had a certain amount of product, how much reactant did you have? So we're going to do some examples of ratios. First, let's go fill in some blanks to make sure we understood these concepts. We saw what a mole ratio was briefly, just a ratio, a comparison between your reactants and products, or reactants and reactants in your chemical equation. And we saw that stoichiometry was all about using those mole ratios to essentially predict how much product could be made, or to predict how much reactant would react with another amount of reactant in different contexts. So that's really all it is. And when we use stoichiometry, we really have to use mole ratios or particle ratios to get to our answer, never mass ratios. That's important to understand, never the mass ratios. So the ratios, we can get them from the chemical equation. Our chemical equation can be viewed in two ways, as we saw. We can view it at the smallest level, the microscopic level, micro meaning small. And if we looked at the microscopic level, basically what we can say is 2 molecules of H2, molecules, will combine with 1 molecule of O2 to produce 2 molecules of H2O, always in this ratio, a 2-to-1 ratio. So if you want to make, let's say, 4 molecules of H2O, you'd have 4 molecules of H2 and 2 molecules of O2, because the same ratio just doubled. Now, at the larger level, the macroscopic level, macro meaning bigger, you can view these as moles instead of molecules. So 2 moles of H2 reacts with 1 mole of O2 to make 2 moles of H2O. That's the other way to look at it. Regardless, it works either way because they're ratios. So again, we can write out a ratio. The coefficient tells us that hydrogen molecules and oxygen molecules combine in a 2-to-1 ratio. Or a mole ratio, you could say 2 moles of H2 for every 1 mole of O2. And you can make conversion factors with that to solve problems. So let's do our first example over here, just to understand how to represent ratios when we're doing problems. So let's look at the first question here. What is the mole ratio of hydrogen gas to oxygen gas? Represented in 3 ways. So hydrogen gas to oxygen gas, don't forget, if there's no number here, it means 1. We always check to make sure our equation is balanced first. In this case, it is. But, always try to see if it's balanced beforehand, because it might not be. So we want to compare hydrogen gas to oxygen gas. One way to write this is to write 2 H2s for every 1 O2. That's one way that you could write it there. Another way that you could write this ratio is simply doing for every 2 H2s that react, 1 O2 will react. So you can write it in this fraction form over here. You can also say 2 H2s to 1 O2. And I didn't put moles or molecules in there, but if you want to specify that it was a mole ratio, to be more specific, you would say, I'm just going to take the same example here, 2 moles of H2 for every 1 mole of O2, just like that. So 2H2 for 1O2, 2 over 1, or 2 to 1. And most of the times we use the fraction form when solving problems, but you should know how to write ratios in these different ways here. And they always have to be the simple ratio, the most simplified ratio. Let's do, what is a ratio of oxygen to water? So we're asking for oxygen to water. And so we can do, we have 1 molecular mole of O2 for every 2 molecules or mole of H2O. And likewise, you could do 1 O2 for every 2 H2O, or you could do 1 O2 to 2 H2O. Again, we typically use a fraction form to solve many problems. You can also write this flipped as well, and it means the same thing. It's just you're writing it in the reverse way. So, for example, or you could say for every 1 O2, you have 2 H2s. And you want to use the correct ratio depending on what your problem is. And same thing over here. You can say or for every 2 H2Os, you have 1 O2. So you can also do it that way. And so your first step before even doing any mole-to-mole stoichiometry problems is really to be able to balance an equation and understand what the ratios mean. We'll do one more just to make sure we understand it has to be simplified. So if I want to do a ratio between H2 and, let's call this example C, a ratio between H2 and H2O, it would be a 2 moles or molecules of H2 for every 2 moles or molecules of H2O. But you would have to reduce it, right? You divide by 2, divide by 2. It's a 1 molecule of H2 to 1 molecule of H2O, a 1-to-1 ratio. That's essentially what that means. So the idea is that if you had 2 H2s, you'd have, 2 H2Os. Or if you had 4 H2s, you'd have 4 H2Os because they have that 1-to-1 relationship that way, right? But if you had 1 O2, it's a 1-to-2 ratio. So if we're looking at O2 here, 1 to 2, if you had 1 O2 has 2 H2Os, if you had 2 O2s, that's 4 H2Os because it's always a 1-to-2 ratio. The H2O is always double of the O2. So I know I'm spending a lot of time on this, but that's super important to understand to move forward into the mole-to-mole stoichiometry problems. So in the next video, we're going to take a look at how to do some mole-to-mole stoichiometry problems. We're going to do a basic skill building note, and then do some real stoichiometry problems following that.